Welcome to Anza Borrego State Park here in Southern California. Today I'm going to be working my way up Fish Creek Wash, which goes through Split Mountain. And we're going to be checking out some of the rocks here. And as you can see, based on these rocks, this is a deposition story primarily. Come geologize with me. So what do we mean by deposition story? Well, particularly sedimentary rocks, right? In this area of Southern California, it's called the Salton Trough, and it has been subsiding for millions of years. And when you have land that subsides and creates a basin, you're going to naturally have sediment wash into that, layer on top of layer on top of layer, especially if the land continually subsides. And you can see evidence of that here. You see layer upon layer of sediment, one stacked on top of the other. This is a subsidence story. This is a deposition story here. All right, I'd like to cut in right here to give you a little bit more context as to why the Salton Trough is there in the first place. So let's go back about 40 million years. This is a great animation developed by Tanya Atwater that I'd like to show you, and it shows you the geologic evolution of the western side of North America. So let's look at some of the key features here. Back then we have the Pacific Plate, which is still around today, and we can see that motion. The Farallon Plate, which is no longer here, but that was there. That oceanic plate was subducting underneath the North American Plate. Where these two plates meet, there's this spreading ridge, okay? So that's where basically oceanic crust is being created because this plate's going this way and this way. All along the western coast of North America at the time, you had a subduction zone. So the oceanic plate was subducting underneath the North American plate. So all along here, you would have had active volcanoes, real similar to the Cascadia region right now. But what we're going to do is we're going to put this into motion. You'll see the millions of years going from 40 all the way to present day. I want you to focus in on right around here, because the Salton Trough is right here. You can see Baja California. But notice the motions as the spreading ridge right here gets subducted underneath. So here we go, everything's normal, we have all the volcanoes, but notice the spreading ridge is going to get subducted under, and notice what happens. Subduction breaks down right there. The Pacific Plate actually kidnaps bits of the North American Plate. It takes Baja California. And you'll see that here. The San Andreas Fault, it activates. Let's pause it right there. So you can see here the subduction broke down. This transformed fault region, this is the San Andreas Fault, started up. The Pacific Plate that we see here actually kidnapped Baja California. It ripped it right off the mainland Mexico, and it kidnapped everything west of the San Andreas Fault, including me. I'm right down here in Southern California. So I'm on the Pacific Plate, and I'm taking a tour up this way. I'm going up. So the Salton Trough is right here, okay? So you can see why there's a subsidence there, right? Because this is getting stretched and pulled. So anytime you do that with the Earth's crust, you start to stretch and pull it, it's going to subside. And when you have subsidence, that's when you get deposition of sediments. So hopefully that helps you get a better context of the macro view of the Salton Trough region. And here's two more images to emphasize the point that there's subsidence in the Salton Trough, okay? So here's Baja California. It's moving away. We can see the East Pacific rise here with these little spreading centers and the transformed faults between them. They run all the way up the Gulf of California, all the way to the Salton Sea region here. So again, here, I like this one. It's not very clear, but I like this one because it tells you the relative motions of the plates. See that? So, but that's not the actual motions. Those are the relative. Actual motions are here. So the Pacific Plate is heading this way. The American Plate heading this way. but the Pacific plate is actually moving quicker, okay? So this Pacific plate is moving quicker away from the North American plate, and that creates a diverging of the plates, right? And if you have that stretching, you're gonna create subsidence and ultimately deposition into that newly formed basin. Okay, let's start by looking at this formation from afar, the macro perspective, right? So what's obvious to me is these bedding planes, these horizontal bedding planes, very indicative of sedimentary rocks, very common obviously. What's also interesting is, do you see on the lower section of the sedimentary rocks down there how there's less rocks within them? Looks like it's more just sand. And then as you move up in the formation, we're getting more and more rocks, or clasts within the sedimentary rock. Some of them really big. Look at that one up there. Okay, so these are just macro observations. You can see also differences in the beds over there, right? So this one looks like it's got a lot more sand in it, and then the bedding above it and below it has a lot more rocks in it. Also, you can see an apparent normal fault there. There's offset in those bedding planes, right? Like these bedding planes once were horizontal, and they've been offset by what looks like a normal fault over there. Okay, great. Great observations from afar. Let's get up a little closer and see what else we can find. Wanted to add a few more details regarding the area we're going to be looking at today. So again, here's a paper about the area here, and I wanted to just review this. It says here that the two plates, that's the Pacific plate and the North American plate, are also diverging slightly, which has caused the Salton Trough and the Gulf of California to open up by oblique rifting and extension during the last 10 to 15 million years. We now know that regional subsidence related to crustal extension and transtension, that's a combination of strike-slip movement and oblique extension of a fault, produced a number of fault-bounded basins that filled with sediments from Miocene to Pleistocene time. So that's what we're seeing here. These are those sediments that filled in that basin. And the stratigraphy that we're going to be looking at today is right here, the Split Mountain Group. So we're starting right here, what's exposed in this canyon, the Red Rock Formation. It'd be awesome to see these Alverson volcanics. I'm not sure if I'm going to find those. And the Elephant Tree Conglomerate. This is exciting. We have some lower megabreccia. Hello. We got Fish Creek gypsum. Got turbidites, and an upper megabreccia and other turbidites. So I think our trip is going to be in this range right in here. So what we see exposed in this canyon wall is the Red Rock Formation and the Elephant Trees Conglomerate. So I think the Red Rock Formation is this lower section here that doesn't have as many rocks in it. And then overlying that is the Elephant Trees Conglomerate. That's at least what the formation's called. Another thing that we notice, again, the stark difference between these beds that are full of coarse sands and the beds above with these big rocks in them, a lot of them very angular. What does that tell us about this basin deposition? Well, it's all about energy, right? So the water or wind, most likely water here, that moved this material was relatively lower energy compared to the water that deposited that later with those big rocks, right? So this is a more low energy environment in an alluvial fan or like a delta system of a river. And then you would have periodic flood events, flash floods, you know, that are very powerful, moving huge rocks. And that's what's indicated by those layers up there. So this is a difference in energy in depositing different types of layers of sedimentary rock. Okay, let's explore this a little closer together. So we can see here that this lower layer actually does have some rocks. There's a layer over here, which we'll check on in a second. It looks more like a mudstone. That might be more of the Red Rock Formation there. And this above it is probably elephant trees conglomerate. It's called a conglomerate formation, but as you can see up there, there's some angled clasts. We'll get to that, but let's take a look closer here. What we're dealing with, we can see, yeah, this is a coarse sandstone with clasts that are some angular, some sub-rounded. Here's a good example of the clasts that we're finding within this. These are granitic, most likely sourced from the Peninsula Range batholith, which is west of here. Okay, so that would be the source. So these are fluvial and delta systems that are filling in that basin. Lower section, not as many rocks, but as we move up, you can see that there's just chock full. This section is actually a great example of the consistency here. And that's a breccia. That is the definition of a breccia. You can see very angular clasts. That's the bits of rock within it, surrounded by the sandy matrix. So what does that tell us? What does a breccia tell us? Well, as you can see, those clasts up there are very angled, which means they would not have been transported from their source rock very far. Because if they would have been transported very far, they should be more rounded. The longer you transport a rock, the more rounded it's going to get. All those kind of sharp pieces are going to break off. So when you have a breccia, or the majority of the clasts have angles like this, you're looking at rock slides, you're looking at mud flows, debris flows, things that are violent and quick. So for example, in this one right here, you can see like it's that thick, it appears. So that could have been just a huge mud flow event coming from the mountains, carrying a ton of this muddy sand and all these bits of rock, breaking them up as they're coming down and depositing them here. Which makes sense. You have subsiding land here, and it's getting filled in with sediment, but sometimes the filling in is quite violent. As you can see, some of these clasts are massive. See those up there? There's a widowmaker right there. Other observations, I believe right here we have two faces of fault planes. You can almost see the slickenlines on this, where they're this way, almost like a corrugated pattern across that face. So you have movement, faults that are sliding past each other. That one looks more like a transformed fault movement there, creating those slickenlines. So that's interesting. Great. There's also a fault right here. You can see this offset. It's a normal fault. So this side has moved down relative to that side. Down here, like I said, looks more like a mudstone. It's got some bits in it too, some sand bits, but not as coarse as this up here. So this is probably that red rock formation. It's got a lot of hematite in it. It's rusting basically, giving it that nice red color. And then above it is the elephant trees conglomerate formation. I just don't like that conglomerate word because I see some sub-rounded stuff here, but the majority of the stuff I'm seeing here is angled. It's a breccia. So this is pretty cool. This is what I believe is a scour and fill feature in a sedimentary rock. So check this out. You have this more reddish bed. Do you see that? And then don't you see this U-shape, more white bed, and it's full of rocks, right? So what does this mean? Well, imagine this bed here is older than this one. So this would have been deposited first, horizontal, just like we see it. Now what this is, it's a scour, right? So imagine we're looking at a cross section of an alluvial plain, and you have this flash flood that's sending like a finger through this alluvial fan, a finger of rocks and a mud flow. Well, that's going to scour or dig into the existing rock in the alluvial fan. It's going to dig into it, remove that material, And then once the energy has subsided, it's going to deposit what was within it in the scour. So it's a scour fill feature. And this one's really cool because we can actually see just how violent this flow was. Because imagine the energy required to move these rocks. These are big rocks. So it was a huge flow, and it just scoured right into that alluvial fan and then filled it in. Scour and fill. Erosion and rock falls still very active here in Fish Creek Wash. But look at this, what caught my eye. More fault plains. See them? With the slickenlines down here and up here and up there, indicating fault movement along these blocks. And the slickenlines are obviously almost horizontal, so these are moving past each other like a transform fault, sliding past each other, leaving striations and polishing each other. And what a beautiful color contrast right here in the sediments.
Gotta get home, there's a garden to tend. All the fruits on the ground and the birds have all moved back to my end. Whistle and static, when the young learn to fly, I will patch up the holes once again.
And on the creek bed, we can see here the clasts from that formation that have fallen out. And as you can see, they're primarily granitic and some metamorphic. Here's another beautiful example of the differences of energy in deposition. So we can see here, we have a very violent deposit right here, right? This is a breccia, angular clast. They're broken up. The majority of it is actually rocks as opposed to the sandy matrix. This is like a debris flow, right? And then right here, you have a relative period of time after this debris flow of more low energy deposits, right? So you got just more sand deposit. And then above that, again, another violent event of debris being deposited, most likely on this alluvial fan. And then after that, again, another period of more lower energy. Perfect example. And look at the size of this clast. Okay guys, I think we're stumbling upon that megabreccia, right? What makes it a megabreccia? Look at the size of this clast in this breccia. It's huge. Look at the size of that one. 6-7 feet across, maybe more, 2-3 meters across. So all this was formed the same way. You just had this violent energy that created this. This is more than just water though, right? This is big chunk of the mountain fell off and came tumbling down the hill. This is a huge rock fall that just shattered into a million pieces and stormed across the landscape. And the reason I can say that is because the material is all the same. It's all that same granitic material. So this all came from the same host rock. So it makes sense that you have this host rock all granitic like this. There's an earthquake, maybe a volcanic event that shakes it, and a huge chunk, I mean, we're talking massive chunk of this mountain falls off and then just goes careening down. And as it's going down, it's breaking up into bits and shattering, and you can see all the bits here. But some of the pieces, I mean, this guy's fractured, but some of the pieces were retained and buried. Huge, massive pieces of it. Megabreccia. You can sense the violent energy that was needed to deposit something like this. This is really special.
Gotta get home, there's a garden to tend. All the fruits on the ground and the birds have all moved back to my end. Whistle and static, when the young learn to fly, I will patch up.
Okay, so we just had a dramatic change in the rock type. So this way is the end of that breccia, some of it mega. These are the clasts of that breccia, all piled up here. But look at right here. The rock type completely changes. Sure, we have beds, but do you see any rocks? Any breccia? Any megabreccia? I see nothing but fine sediment beds. Let's consult the paper and see if we can figure out what's going on. Okay, so let's review. We've already checked out the red rock formation and then the overlying elephant trees conglomerate, those layered breccias that we saw that were so beautiful. Didn't really see any Alvarezson volcanics to speak of. I believe we saw at least a section of this lower megabreccia with those massive clasts. But notice this, the Fish Creek gypsum. I didn't see that, but after that, it shifts to sandy turbidites. Sandy turbidites. So you can see here that there's a transition from non-marine to marine, which is interesting. And now I'd like to just read this paragraph from the paper that explains it so well, what we're seeing here. So it says the Fish Creek gypsum and laterally equivalent lower Latrania formation record a rapid transgression of marine waters that apparently was controlled by a change in the regional tectonic regime. Onset of late Miocene rifting and high-angle normal faulting recorded in the Split Mountain Group may have been related to early movement on the West Salton Detachment Fault System, or it may represent a distinct earlier phase of extension that predates detachment faulting. In either interpretation, it appears that a major tectonic change at about 6 to 7 million years ago produced nearly synchronous marine incursion throughout the northern Gulf of California and Salton Trough region. This incursion flooded an area at least 400 kilometers or 250 miles long from San Felipe, Mexico in the south to San Gorgonio Pass in the north. Wow. So the way I interpret that is, again, we're talking about this region subsiding continually, right? So based on that, it sounds like there was a tectonic event of some sort, perhaps a massive earthquake, and you had a huge settlement of the region. And then the actual ocean from the Gulf of California encroached and flooded it all the way up to San Gorgonio Pass, which is so far from here. So this whole area just got flooded with the ocean, which would make sense that you are going from a breccia, a more alluvial fan, non-marine deposit. By the way, look at the size of this clast. Holy smokes. It's the size of a small car. Sorry. So you go from a non-marine deposit, and then it gets flooded by the ocean, and then you get marine deposits, or the sandy turbidites deposit on this side. Very interesting. Very cool. Breccia, sandy turbidites. Non-marine, marine. So I mentioned sandy turbidites. What's a turbidite? Well, a turbidite is, again, it's marine. It's a marine deposit. So imagine a river going out into an ocean. There's going to be, obviously, the alluvial fan on the non-marine side, and then it's going to feed into the ocean, and you're going to get not big rocks out there, right? Those are all out of suspension at the alluvial fan section. But out into the ocean, you're going to get the sand and the lightest silts and muds out there that will deposit, okay? So what can happen is when you have a river going out into the ocean, that sediment builds up and then it becomes unstable. And you'll have these basically underwater landslides, but they're turbidity currents. So that sediment kind of fails and it starts sliding, and this is all underwater. And it'll deposit these layers that will be lithified, and they're called turbidites. This is a good example of one. So you can see, for instance, right here, this is more coarser sand. So when you have a turbidity current going down, the coarsest particulates within the turbidity current are going to fall out of suspension first, right? So the coarser sands are going to fall out of suspension first, and then once those are settled, the muds are going to come down and deposit on top. So you can see that there's a layer of mud here. So that's one turbidite there. And then you had another turbidity current that came through and deposited more sand right here, and then it was capped with more muds and silts here, okay? And then you had another turbidity current come here, deposit all the sands, and then a little cap of the silts and the muds here. And a bigger one right here. Now, this is fallen, it lost its cap, but it's a very recognizable pattern. And this is very common in marine environments, which is what this is, turbidite. Again, here's a closer view of the turbidites. Again, you see you have a layer of sand capped with the finer sediments on top. Layer of sand capped with finer sediments on top. Cool features here that you can see. See these little bits here? And it's better over here. Check this out. Okay, so think about that. Imagine when this turbidite was deposited, right? So this was the bottom of the ocean at the time. And then this one came through. And these are somewhat violent, they can be. And you can see how this turbidite, this sand coming through, actually pulled and ripped up pieces of this and entombed it within itself. These are called rip-up clasts. And they're really cool to find. So you can see a bunch of them here. So these pieces are from the top of this turbidite, but they're included in that one. Rip-up clasts. Man, do you think that made a thud when it fell? I better not overstay my welcome. Here's a handsome section of the turbidites. Just gonna think out loud here, but notice these sections. See these beds here? And you kind of follow them, and then they just get destroyed right here. It looks like there was some sort of deformation. You can actually see a trend where they actually go straight down and curve under. You can even see some, it looks like they broke. You see this sandstone layer here? It continues here. It looks like they were pushed and shoved in there. You see that? And there's more evidence of deformation over there too. I think that's called thickening, when you have these beds that are getting kind of deformed and almost like thrust on top of each other. And this one's pretty interesting because it actually broke through, it looks like right there. Let me get you a closer look at this because it's actually pretty cool over here too. Yeah, right here. So you can almost see how the beds are thrusting over existing beds. And then over here, you can see how they curve down. Something going on here. They've been under a lot of pressure or just deformed. Let's see if I can get that trend over here. Yeah, so here's the beds here, kind of just get tweaked, but you can see how they curve down and this way. And then a little bit of it gets injected up there. It's like toothpaste. Okay guys, I don't even know how I'm going to introduce this to you, so I'm just going to show you. There's my Jeep for scale, and you'll see why I need that size scale for what we're about to see. There's our marine turbidites. Nice and horizontal. But check this out. Oh my word. What happened here? Okay, so let's just make some observations, right? So we got the turbidites over here, pretty well horizontal, no big deal like we've always seen. But then something dramatically changes right here. You see this form, this arch form, that's called an anticline. So these beds that were once horizontal have been compressed and arched up. We also see above that, this part up here too is arched up and wraps back down. So we have a couple anticlines. We have just a jumbled mess of those turbidite beds. We see how this one got thrust under and that one's over. Okay, and then looking over here, we see this chaotic mess. There's no rhyme or reason to any of that. It's just a chaotic mess. From this angle, it looks like a breccia. And it's right against our turbidite beds that are fully deformed. So what's the story here? So what geologists thought happened here is a massive rock slide. We're talking gargantuan landslide. These things are called sturzstroms. It's a German word, literally means rock flow or rock stream. Now this is just a gargantuan rock slide. We're talking a huge amount of a mountain falls down, not only vertically and shattering, but it actually will run horizontally across the landscape for miles. And that's what they think happened here. This is the deposit of that sturzstrom, this chaotic mess. It came off that mountain, came down at high speeds, went across the landscape, went past and over the alluvial fan, and impacted the soft sediments in the ocean at that time. Yes, they were soft sediments. As you can see, they're bent, forming this anticline. They took all that energy, this high energy rock flow, boom, took it all, and it just bent them to bits. And it's just so beautiful that that event is just solidified, pun intended, right here for us to enjoy.
I can't believe that my lime tree is dead. I thought it was sleeping, I guess it got fed up from not being fed. But I would be too, I keep food in my belly and hope that my time isn't soon. Isn't soon. So I try to understand what I can hold in my hand, and whatever I find, I'll find my way back to you. And if you try to find it too, 'cause this place is overgrown, it's a wax and bone. Home is wherever we are, if there's love here too.
I'd like to read you the words of Dr. Pat Abbott, a geologist, reading from his 1996 guidebook of this area. And he puts it so well with this. About 5 million years ago, a great earthquake shook 300 million cubic yards of rock from the steep face of the Fish Creek Mountains. The mass fell, shattered on impact, and flowed at high speeds for 7 miles to the northwest toward the Vallecito Mountains. Lobes of rocky debris detached from the fast-moving mass and injected downward into the sediments on the seafloor, pushing and buckling the sand layers into the anticline in front of you. Today, some of the once fast-moving rock debris that caused the anticline is exposed above and alongside it. And you can see that over here to the right. That's that huge chaotic mess right there. That's the sturzstrom deposit there. And here you can see the soft sediment deformation of those marine sediments that were impacted by that gargantuan rock slide.
The back of my house is a trail that won't end. We went walking so far that it grew back in. Now there's no trail at all, only grass growing tall. I'll get on my machete and battle with time once again.
Now I know what a lot of you are thinking, like, get close to the outcrop, I want to check out what's going on. And I got you, I'll get close, but this formation is just so massive that you lose the details when you're so close. But let's do it anyway. Okay, so here's the sturzstrom deposit. Most likely a megabreccia. But you can just see it's just a chaotic mess. No rhyme or reason, just a mess. And what's great about this is look at that. You can actually see and put your hand on the contact of the rock slide hitting the marine sediments. Should we do that? Right there. Wow, that's incredible. Okay, let's see what else we see here. Beautiful deformation, soft sediment deformation. So this is one side of the anticline. Let's see if there's any details. Okay, so same turbidites that we'd saw before. This is more soft sediment in here, softer sediment than the sandstone. Oh yeah, look, it kind of got squeezed and thickened right there, and then it pinches out. I mean, that's right at the impact zone. All right, here's that anticline. Beautiful. Look at this deformation here. Thickening and thrusting, just a mess. The amount of energy that these marine beds were put under is just amazing. So this is the left side of the anticline coming down the arch, and then it just has this really tight fold right here. Oh, this is kind of cool. Look at these little laminated layers just all faulted. That's definitely from impact. Oh, more rip-up clasts within that. Those were in there before this huge impact. It's crazy up close, huh? And then it just goes back to horizontal. I know it looks like a fold right there, but that's just inset. It goes in and out, but that's all horizontal. Had to back up. I lost the details that close up. It's hard to follow. I really like this fold right here. And then this section right here where the sediments are kind of getting thrust over each other. Trying to make room for this high energy impact. So here's that main anticline. And check out like at the bottom of it. This poor sandstone just is shattered. Can you imagine the amount of energy this thing endured? Just that impact, just shattered it. Now you might be asking, wait, if the Salton Trough is constantly subsiding and more sediments coming in, then how do we see these today? That's a great question. Well, 25 million years ago or so, the San Andreas Fault was activated, and certain strands of that fault right now, the Elsinore Fault and the San Jacinto Fault, are wreaking havoc on these sedimentary rocks and breaking them into blocks and lifting them and twisting them. So they've been uplifted since then. That's how we're able to see them today. And that's what I just really enjoy about geology. You learn about geologic time, and it's just unfathomable how much time it takes for things to happen. Millions, hundreds of millions, sometimes billions of years for things to happen. And then you have things like this. This event, what? Took maybe a couple minutes, you know, maybe less than that. And this was created in just seconds or minutes. And that's what I just love about geology. It's just one extreme to the other. You can be baffled by billions of years in the sediments and different formations, and baffled by seconds to minutes in some of the same formations. Well, I really want to thank you for joining me as we explored Fish Creek Wash here in Split Mountain in Anza-Borrego State Park. I think the theme of this video is deposition, right? And we saw extremes. We saw low energy deposition, like those finest layers on those turbidites, all the way to the highest energy deposition, that of the sturzstroms, these huge rock slides that impacted this area and helped create beautiful geologic structures that we enjoy here. Thanks again for joining me. We'll see you on the next one.
There's love here too.